All right, hello everyone. In this video, we're going to look at an alternative method that we can use to make our short-term time series forecasts that's similar to the moving average model, but is a little bit different in how we'll apply it. And that's called the exponential smoothing model. And so basically, the idea here is that, all of these short-term forecasting models we're creating make their predictions into the future based on the previously observed data values that we have in our data sets. And so with the moving average model, the, the number of periods that we're using in that moving average essentially determines how much weight we're distributing across the previous observations. So for example, in our 4-month moving average model, we basically are evenly distributing a quarter of the weight across the previous 4 observations. But in some cases, we might want to be a bit more deliberate about how much weight we place on the more recent observations versus observations that are further back into the past. And so in order to do that, what we can do is introduce something called a smoothing constant that we can adjust between the values of 0 and 1. And then we can use that to indicate how much weight we should put on the more recent observations going back into the past. Should it be very high or should it be very low? And depending on what your underlying kind of baseline model looks like, that will have some influence in the types of values that you would want to use. And we'll explore that a little bit more when we get into our example here in just a moment. So coming back and taking a look at our 4-month moving average, we had seen that the forecast value was quite low compared to the previous forecasted value. And again, we're weighting the forecasted value really based on these previous 4 months in the sliding average window. And so what we might try to do is to say, well, perhaps we can put more emphasis on the more recently observed values. And so to do that, let's just start by copying this into a new location so that we can create our exponential smoothing model. So I'm just going to grab all this, similar to what we did to create the 3-month moving average model below. I'm going to just copy this, and we'll do this in a side-by-side. So I'll paste it here, and then we'll update this to be an exponential smoothing. All right. And so what we need to do is make some adjustments. We're no longer going to have an average for the previous observations that we're going to track. We're going to have a smoothed value. And the smooth value is basically like our best effort to determine what we think is the average or the mean going forward. So rather than strictly basing it on a previous number of observations, we're going to try to smooth or adjust that mean to better suit our purposes. And we'll talk a little bit more later about how we might make a decision to go in and kind of reset the smooth value in cases where we see the model has got some trends or greater fluctuation than maybe we had anticipated. So let's just, we'll leave the error messages for now because we can clean that up after the fact. But I'm going to change this column from A for our average to S, which is going to then represent our smooth value. And we need to introduce an additional parameter here, which I'm just going to call alpha. Okay, and we'll just default to a conservative value of 0.2. Alpha will be our smoothing constant, right? So this is going to be a value that it lies anywhere between 0 and 1, and we'll make some adjustments once we get this set up so that we can see what this looks like. So this is an input. We'll update it as such. And so what we need to do here now is make some adjustments. Our smooth value in the first case is just going to be equal to the first observation that we have. We don't have any historical data going back further than this, so we can just set this equal to the current value. And then similar to what we did before, where the average value becomes the forecast, that's what's going to happen in this case. Our smooth value will become our forecast in the next period. But where things are different is in the calculation. So I'm just going to get rid of these. And so now we can go ahead and create our first smooth value. And again, it's really a matter of determining how much weight we want to place on the current observed value and how much we want to put onto the previously smooth average value. And that's where this alpha variable comes in. So our first smooth value is going to be equal to our smoothing constant. So in this case is Q2. Now we're going to copy and paste this formula down through all these cells. And we don't want to use a relative cell reference, because once we do that, it'll just update from Q2 to Q3 to Q4. So make sure you change this to an absolute cell reference by popping in the dollar signs. And so we want to have our smoothing constant, and we're going to multiply that by our current observation. So in this case, it would be N6. So basically, if you want to think of it in terms of percentages, we're taking 20% of the currently observed weight into account, and then we're going to add that to the difference. So we're going to take 1 subtract our smoothing constant. So we're taking 20% and applying it to the current, and then we're going to be taking 1 minus 0.2, which is 0.8 or 80%, and we're going to apply that onto the previously smooth value. So this will constitute how much we're taking from the current observation plus how much we're taking from the previously smooth value. So this will be 1. Again, make sure you put your dollar signs in here to indicate we have an absolute reference. And we're going to multiply that by our previous value. For some reason I can't get in here, so I'll just type it in. So this will be 0.5. Okay. And so once we've got that, you can see the formula here, we've got a new smooth value. And again, these smooth values will then become the forecasts in the following period. So once that's done, you can just go ahead and copy that down into the remaining cells. And we'll clean up these decimal places in a moment here. And then here we had taken the forecast from the previous column and row. So we can just copy and paste these values kind of back up. So I'll use a fill handle, just pull these back up through so we get everything filled out into the table. And then I'm just going to update the formatting here to get rid of our decimal places. And we can do the same thing here for our forecasted value. There we go. Now that we have built this model, we can investigate it and compare it against the previous models that we had built up here. And so this is where these accuracy measures come into play. With an extremely low alpha or conservative alpha value, we can see here, we're really not placing much emphasis on the most recent observations, right? Only 20% is being applied to the actual observed values. And 80% is being applied onto the previously smooth constant. And when we look at our accuracy measures, we can see that compared to, for example, our 4-month moving average or our 3-month moving average, this model is not performing very well. Our root mean square is about 3,700. Here we're just about 3,000, and here we're even better at 2,621. And so what we can do is we can make adjustments to this to say how much or how little do we want to put our faith in the most recent observations. So for example, if we increase this to 0.6, we can see now we've dramatically updated or improved the forecast value, and we've also had quite an effect on our accuracy measures. So the root mean square error now is 2,100 approximately, which is now beating our 3-month moving average model, and of course leaps and bounds ahead of our 4-month moving average model. So these accuracy measures now give us some type of a language that we can use to compare different models to make a determination of which one is best. And so some of you might be looking at this and thinking, well, why don't we just go up even higher, because we can see the last observed value at 380 is still lower than that. So going into the future, I would expect a value that's greater than 380, but we're not going to get that. And this is actually due to an underlying assumption that we've kind of implicitly made, which is that we're looking at a somewhat stable average across our data. But when we visualize it, we can clearly see that that's not the case. There are, in fact, some trends in the data that we're not accounting for. And the moving average and the exponential smoothing models don't allow us to account for trends. And in order to do that, we have to add something else, which we'll look at in the next video. But really briefly, what we can do is just take a moment to visualize this, and we can see what's actually happening in a chart, which sometimes helps make it a little bit more easy to understand. So let's take our data here. I'm going to go across these columns, and I'm going to insert a chart so we can see both our actual plotted observations, our smooth values, and our forecasts all in one location. So we can just insert a line chart. Oops. And then I'll just grow this out so it's a bit easier to see. All right, here we go. And so now with this, we can see where in the blue line here, this is our actual observation data. And then the orange here, this is our smooth value. And then in the gray, our forecast. And again, the gray is really just one step into the future. We've taken our smooth values and pushed them forward one period to get our forecasted values. So we can see here that our forecast is, again, quite low compared to where we would expect maybe to see this. Now, that is not to say that it wouldn't happen. We can see that, housing prices can drop dramatically. So, for example, in this case, we do see a steep incline in the price period over period, but then a dramatic decrease. So it's possible that this could happen. The question we have to ask ourselves is how likely is that to happen? And again, there are maybe some outside environmental influences that we aren't considering, but it's difficult to know. In either case, what we can see is that there are definitely kind of smaller trends within the data. So a slow decline here and then a steep incline trend in the data at this point in time. And right now, our models can't account for that. If we make adjustments to alpha, we can go back and see what this looked like with the 0.2. We can see that the updated chart reflects now, right, this very, very low inclusion of the most recent observations. And we can see here that we're out quite a bit. We've got a smoother average through the data, which is what we would expect, but is not maybe the best for accurately making forecasts for our given data set or our given model. So again, use charts to help visualize and get another way to look at the data to help you understand what's going on. And if the numbers aren't working, a lot of times visuals can help make sense of what it is you're dealing with. But here we could see if this was our next forecasted value. I mean, again, that's very, very low. I would, looking back in the recent data, I would suspect that this is probably not likely. Looking at the trends, we probably do want to put more weight on the more recent observations. So that would lead us to update, like I say, our smoothing constant. Now, one thing you want to be aware of here is, not to push it all the way to the outer bounds. So for example, you might just say, well, why don't we just base it on the previous observation? So if we go with a smoothing constant of 1, that's really not giving us any kind of predictive value. As you can see here, all we're doing is saying 100% of our forecast is going to be based on the previous observation. So you'll notice here, our observation values just now become the forecast values, and we're kind of bypassing this smooth average altogether. And so all we're doing is taking the observed data and saying, well, next month is just going to be the current, which I don't think is going to give us a lot of value, right? Anyone could have just decided that's what we want to do. We don't need to build a model for that. So the thing that we need to account for is, in this example, really the trends that we see in the underlying model. And we'll tackle that in the next video by implementing something called Holt's linear trend method.